Welcome back. This is the second of two videos for Part B of Week 1 material. First thing we're going to talk about in this video is the other direction. So if you have a binary number, how do you convert that into a decimal number? Now this direction I actually think is easier than the other direction, so if the other direction made sense, you're in good shape. Alright, so let's start with an example. We'll start with the binary number 1010. Alright, so again, this is a number in base 2, and we want to convert it to base 10. So we're essentially going to do the same thing, but in reverse. So if we go ahead and draw out our little tables again, so we'll split it up again into two halves of the screen. Up here, we'll have our base 2 number this time, right? Because we're starting with base 2. Down here, we'll have our base 10. Alright, in our base 2 number, we have 1010. So if we're going to represent that in our little table, it looks like this. So this is the 1s. This is the 2s. This is the 4s, and this is the 8s, right? Again, that's just going by powers of 2. And we have 1, 0, 1, 0. Alright, and what we want is to know what this looks like as a base 10 number. So again, base 10, 10 to the 0, this is the 1s, 10 to the 1, this is the 10s, 10 to the 2, this is the 100s. So we want to convert this base 2 number into this base 10 number. So with this direction, all you really have to do is add up the places where you have a 1. So we have 1, 8, right? We have 1 in the 8 spot. We have nothing in the 4 spot. We have 1 in the 2 spot, and nothing in the 1s. So we have 8 and 2. That gives us 10. That's it. Like I said, this direction, much easier, right? So again, 0 in the 1's place, 1 in the 2's place, so we add a 2. 0 in the 4's place, 1 in the 8's place, so we add 8. So the binary number 1010 is the number 10 in decimal. Alright, go ahead, work on this one on your own. So go ahead and do this on paper. The binary number, again, this is in base 2, is 11011. Go ahead and convert this into a decimal or base 10 number. And when you're done, unpause the video. Alright, so going through the same process, again, the rule is you go through all the 2's places. If there's a 1 in that place, add that power of 2, right? So starting on the right side this time, because why not? There is a 1 in the 2 to the 0's place, right? There's a 1 in the 1's place, so we add 1. There's a 1 in the 2's place, so we add 2, so our total is 3 now, right? Because 1 plus 2. There's nothing in the 4's, so we skip that. There's a 1 in the 8's place, right? So we add 8. So now we have 8 plus 3, which is 11, right? So we have 11 total now. We move to the next place, which is the 16's place. And there is a 1, so we add 16 to the 11 that we had before, which means we now have 27, and that's the whole number, right? Because we've gotten to the last place. So again, because there's a 1 in the 1's place, a 1 in the 2's place, a 1 in the 8's, and a 1 in the 16's, you add up 1, 2, 8, and 16, and you get 27. So the binary number 11011 is the decimal number 27. So I'd like you to go ahead and take a couple minutes and write down an algorithm for converting from a binary number to a decimal number. Alright, so this is something that you should write down. You can do bullet points if you want, but keep in mind, algorithms should be unambiguous, meaning there's no guesswork involved, right? Executable, meaning they need to be able to be carried out in practice, and terminating, meaning at some point they need to end, right? So keep these three characteristics of algorithms in mind while you write down your algorithm. And also keep in mind, this should be a general algorithm. It should work with any number. So it shouldn't work with just that last example. It should work with any example that I give you. If it helps, you can say, you can limit it to a largest number, right? So if you want to say, oh, the largest number it can do is this, if that helps you with your algorithm, go ahead and do that. But go ahead and take some time now, pause this video, write down an algorithm for doing this, for converting a binary number to a decimal number, just to get some algorithm design practice in. And then when you're ready, go ahead and come back to this. Alright, so hopefully you spent a little bit of time writing down your algorithm. That said, I want to talk about just sort of practical logistics for this course. For this course in particular, the largest power of 2 you need to know for these conversions is 2 to the 5th, which is 32. So I'm not expecting you to know every single power of 2, because there's an infinite amount, right? So again, the largest power of 2 you should know is 2 to the 5th, which is 32. What that means is the numbers that you need to be able to convert between binary and decimal are the decimal numbers between 0 and 63. Specifically the integers. Don't worry about floating point numbers. Just worry about integers between 0 and 63 inclusive. Where did I get the 63? Well, the largest number you can represent with a 1 in the 2 to the 5th spot and the 32nd spot in binary would be 1 1 1 1 1 1 in binary. It's 6 ones. There's a 1 in the 2 to the 5th spot, there's a 1 in the 2 to the 4th spot, there's a 1 in the 2 to the 3rd spot, a 1 in the 2 to the 2nd spot, a 1 in the 2 to the 1 spot, and a 1 in the 2 to the 0 spot, right? And that number is 63 in base 10. So again, largest power of 2 you need to know is 2 to the 5th. Don't worry about the other ones. If you need any clarification on this, please let me know. Post on the discussion forum or send me a message on Canvas. Alright, I do want to take some time to talk about other bases, right? So even though obviously decimal is very important to us as humans, and base 2 is very important to computers as electronic components have the two states on and off. But I do want you to just sort of keep an open mind about this. There are other bases, and you could write numbers in any base that you want. You could take your favorite number and represent any number using that base number, right? You just follow the same sort of rules about how to set up the places and go from there. That said, I do want to highlight 2 other bases that you should know about for this course. Other common bases are base 8 and base 16. So base 8, these are called octal numbers. Base 16, that would be hexadecimal. The reason why these are common bases is because these are the best compromise between computers base 2 and humans base 10, right? If you look, 8 and 16, those are the closest powers of 2 to 10. So these are pretty common in the computer science world, so I wanted you to at least know about them and be introduced to them. So again, base 8 are octal numbers. And as you can probably guess, base 8 numbers, octal numbers, uses powers of 8 as the places, right? So the first place would be 8 to the 0, next one's 8 to the 1, and so on. Octal numbers use 8 digits, right, which makes sense. Base 10 numbers, decimal numbers use 10 digits, binary numbers use 2 digits, and so on. So the 8 digits in octal numbers are 0, 1, 2, 3, 4, 5, 6, 7. And then the other number system that I want to introduce is hexadecimal numbers. So these are numbers that are in base 16. All of the places for these numbers are powers of 16. And it has 16 digits. Alright, and this is where it starts to get a little bit weird. So the 16 digits that hexadecimal numbers use are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now here's where it gets interesting. We can't use 10 as a digit, right? Because 10 is made up of 1 and 0, which are 2 digits already, so that just doesn't work. So the standard to represent the decimal number 10 in hexadecimal is to use A. So A here is the next digit, B is the next digit, C, D, E, F. So the decimal number 15 in hexadecimal is F, which again is kind of weird, right? Because we're using letters as numerical digits, but that's just how it works. And again, the reason being is because you can't really use 10, 11, 12, 13, 14, 15 as digits because they are made up of 2 digits themselves. You may have seen these if you have done any sort of web programming before, or if you've ever seen hex color codes, right? They sometimes have these weird letters in them. This is where it comes from. It's from this hexadecimal number system. So again, if you have any questions about this, either about doing the conversions or any of these other numerical systems, please let me know. Post on Canvas on the discussion forum or send me a message. Thanks for watching.